Welcome, everyone. Good afternoon. Today it is a pleasure to welcome Hector Socas-Navarro for today's talk. As you know, he's an staff researcher at IAC. He's working mostly on solar physics, although he does some excursions from time to time. At least I have read one paper of his in cosmology. So he likes testing other fields. And she's currently also taking care of the Museo de las Ciencias, the Science Museums just aside the IAC headquarters. So you have like 45 minutes for the talk, and then we're going to have some short discussion. I remind everyone that I will try to mute all of you, and only at the end of the talk we'll have some time for the discussion. You raise hands, and then I will unmute you. Okay. So Hector, ready?
Yeah. Sorry, I have a question. You said I have 25 minutes.
No, 45.
45. Okay.
I meant 45. Sorry.
Okay, I had a little panic moment there.
No worries.
Under 25. Okay.
We're flexible. You may run into the question time if you need to a little bit.
Okay, thank you very much. I'll try to not to take that much, but I'm afraid it will probably be more than 25 minutes. Thank you all for coming, and I'm very excited to tell you about this work. Let me share my screen here. And okay, I hope you can see my screen. This is actually a paper that is coming out soon in Astronomy and Astrophysics, but you can find it already. There's a preprint on the archive, although it's not exactly the same version that's posted on the archive, but close enough, I guess. And this is a work that I did in collaboration with Andrés Asensio. And you can see that the title is quite long, and that's because it's almost like two different papers. One is about, the first part is about a new tool that we think might be very useful for the community. And the second part is about the findings that we encountered when we started applying this tool to observations. We even considered at some point to split it up into two different papers, but in the end we thought it would be less work to have everything in one paper. So it's a little long, but yeah, I hope that you will like it if you read it. Let me start with a bit of introduction, and perhaps we should start with the motivation of why we have been working on this. And in fact, a lot of people in my field have been working recently on trying to develop these kind of new analysis tools basically for spectroscopic and spectropolarimetric observations. The main motivation has to do with this, and this is a very general problem in astrophysics. What we have are observations typically of a spectrum of the sun, of a star, or many spectra, and this is what you have. But what you are interested in is the physics of the atmosphere that is underlying that. And so the way that you go from, in order to go from a model atmosphere to the spectra, you do spectral synthesis, and this is fairly well established, and in most cases we know how to do this pretty well. But then there's the other problem, how you go from spectra to model atmospheres. And this is what we call inversions, but the name is not standard. Other fields, they use different names for these sort of things. Mostly what we do in the solar community, most of the time, is a iterative fitting procedure, where you basically start with a guess model atmosphere, you compute a synthetic spectrum, and then you compare that to the observations. If they match, then that's great. You've done your job. You have the model atmosphere that is compatible with that spectrum, but in general they will not match, and so that's where you have to do some magic that will give you some corrections that you need to apply to this model, and then you get a new model that is better. So the synthetic spectrum from that model gives you a better fit to the observed spectrum, and then you iterate that as much as you wish or you can. This is sort of the traditional approach to this problem, and I think, like I said, it's a very general problem that you encounter in astrophysics. And this approach has been working well for a long time, but it has some problems which are becoming more and more important in recent years. So you have to deal with degeneracies, the fact that you might have different combinations of physical parameters that give rise to the same spectrum. These techniques tend to be slow depending on the problem that you're solving, but in some cases it can be prohibitively slow for some applications. And also you have stability issues, meaning that because it's a minimization algorithm where you start from some point and then you try to work your way to the minimum, you don't always you may get stuck in secondary minima, or you might find that somebody else starting from the same initialization on a different machine with different computer and libraries, they might encounter a slightly different solution, or even a completely different solution altogether, depending on the degeneracies and things like that. So these, in spite of these problems, this can give very good results for some applications. But we are facing more and more the problem where the new instrumentation in the field of solar physics is delivering massive data sets, where you have really huge amount of spectra. We are talking about observations with spatial resolution, with very high spatial resolution. So for each pixel in your image, you have a spectra, and you have to work with very large data sets. And so at some point, this becomes prohibitive, and so the development of this new instrumentation and these very large data sets is driving the interest in exploring alternatives. And I think this is true in many areas of physics. And one of the alternatives that is often proposed whenever one has pushed a technique to the limit is use machine learning, because machine learning is very amenable to dealing with large data sets, which is a typical problem nowadays in science in general. So in particular with artificial neural networks, which is what we have used in this work, I think it's a very promising avenue. Actually, the first applications to this problem of the inversion in solar physics, it started at the beginning of this century. That sounds really nice. I like to say at the beginning of this century to refer to the early 2000s. And there were some exploratory works. I did some work on that too, and that was very promising. But these kind of techniques never really never caught on in the community, and I think that's for two reasons mainly. One is the problem of the filling factor. We try to make inversions where the magnetic field is a very important parameter to retrieve, and especially in the a couple of decades ago, the observations typically had resolutions of roughly the order of an arc second, and at that kind of spatial resolution, you're not resolving the magnetic field structures, which are much smaller, and so this filling factor, how much of your pixel is filled by the magnetic field, this created a problem for this technique. And the other reason, I think, is that the algorithms are complex, and there were not a lot of tools available that could help you to get started. So 20 years ago, you basically had to code everything. Remember coding neural networks in Fortran, everything, the training algorithm and everything, and so that's hard to do, and it's very time consuming and prone to errors. It's difficult to do it if you're not used to working on that. But like I said, that was 20 years ago, but things have changed enormously in these 20 years. And currently, I think the field is blossoming and there's new opportunities. And if you look at the literature recently in these kind of problems that I've been talking about, there's been lots of papers published in the last 2 or 3 years with many new advances and ideas and tools that have been developed. And the reason for this renewed interest, I think, is there's two reasons. One, well, basically because these problems that I mentioned earlier have been not resolved, but they've been mitigated to some extent. So this problem with the filling factor, it still exists. Nowadays, we have much better observations with a much higher resolution, but still we are not resolving the fundamental scales of the magnetic field. But the problem has been mitigated. It's not as bad as it was 20 years ago. So I think you can do more. You can do interesting things even in spite of that. And of course, there's been the big revolution of machine learning everywhere, which has exploded. And now there's so many tools. There's a lot of open software and a lot of libraries. You can do a lot of stuff in Python really easily. So a lot of people have got involved and in this in machine learning, and you know, just because there's this extensive library of tools available, then that simplifies your problem a lot. The data that I'll be talking about here comes, it actually comes from one source, which is the Hinode satellite. This is a Japanese-led mission with collaboration from NASA and also the European Space Agency. It was launched in 2006. And one of its instruments is a spectropolarimeter for solar observations, which records data like this. What you can see here is an image of the spectropolarimeter. This instrument basically is a slit spectrograph that scans the solar surface by scanning the slit. You build a raster of slit spectra, and here you have in the vertical direction is the spatial direction. So you have like brighter and darker points here. This is quiet sound. So bright and dark is the granulation. Bright points are hot granules, and darker points are cooler intergranular lanes. And the horizontal direction is the spectral dispersion. So you have here two spectral lines. It's a very, very tiny spectral window. It's about 2 angstroms. This is very high spectral resolution observations. It's about a 2 angstrom window. And you have here two spectral lines. You can see the line shifted to the left and the right in the according to the granulation. And then here you have a sunspot where you have a magnetic field, and it's darker in the spot. So this is intensity, and this is Q, U, and V is the polarization, linear and circular polarization, where the gray background means no polarization, and black and white means positive and negative values, according to some reference frame. So we wanted to develop this tool that will work for Hinode, which is a very popular instrument, but also for the new DKIST telescope, which is the large 4-meter aperture solar telescope that's been built in Hawaii on Haleakala, on the island of Maui. And this telescope will have, I believe the instrument is under integration right now. It will have a spectropolarimeter called VISP, which can do something similar to this. Well, there's some differences, of course, between these two instruments. As usual, the ground-based instrument will give you much more flexibility. You can have many more configurations. You can observe different spectral regions. But what's important here, the reason why we focus on these two is because, you know, this is the sort of where you're pushing the spatial resolution to the limit with current capabilities. Hinode gives you a spatial resolution of about 0.3 arc seconds, these kind of observations, which for spectropolarimetry is pretty good. And there's a very large library of observations available already on the web that you can download. All the Hinode observations are publicly available. And with DKIST, the visible spectropolarimeter, the VISP, it will have nearly an order of magnitude better spatial resolution. It's going to be in this spectral region, it's going to be about 0.05 arc seconds. So that's going to be tremendous. It's going to be really, really great. So we're really looking forward to that. And of course, these instruments, you have this problem of very large databases where, you know, it's very difficult to make very sophisticated inversions of the data. And so we thought it would be a good application for our technique. This is just to show you some profiles of the data that we're going to be looking at. These two lines that I mentioned earlier are very popular lines in the literature in solar physics. These are neutral iron lines at 6301 angstroms, and yeah, the data, the average over a quiet sun region looks more or less like this. You can see here. This model, this neural network model that we built is publicly available. We set up a repository in GitHub where you can go and download all the code and all the tools with instruction how to use it. At least the Hinode part, because we, like I said, we have trained 2 different neural networks to work with these 2 instruments, Hinode and DKIST visible spectrophotometer. But the thing is that we still don't have any even validation observations from DKIST because, well, because of the pandemic, things have been more slowly in this last year than expected. But we hope it will be soon. So, there's probably some fine tuning that we will, let me put it this way. We don't feel comfortable releasing to the public the tool before we've had the opportunity to test it with actual data and make sure that it works. So that part is still pending. But in principle, you could take what we have for Hinode and just tweak it to work with DKIST. We've actually built the model also for DKIST using the simulator that they have. There's an instrument simulator where you can get all the configuration parameters and get all the information that you need. But there's always something when you go to real data that it's not as expected. So we're going to wait a little bit until the first data becomes available and we can test it and make sure everything works. But like I said, the Hinode part is publicly available there, so people can go download it and start applying it to this extensive library of observations that we already have for Hinode, which is, I think, very nice. So some details about the neural network. It's a multi-layer perceptron with 6 hidden layers. And there's 300 neurons per layer. The input layer has 112 neurons for the case of Hinode and 175 for the case of DKIST. But just because these are the input wavelengths, this is the sort of your spectral profile that you provide here as input. And then the output layer has 9 neurons, which are the model parameters that we want to retrieve. And these model parameters are, we have 5 parameters that describe the temperature. And these are temperatures at 5 different heights in the photosphere, starting from log tau equals 0, which is the sort of the base of the photosphere. That's where the continuum is formed. And then -1, -2, -3, and -4 are just different optical depths above it that you can probe, because that's the formation region of the spectral line. Then there are 3 parameters that describe the magnetic field. And we assume that the magnetic field is constant with height. So we only retrieve an average of the magnetic field in the line formation region. And then another parameter, which is also a constant Doppler velocity that controls how much our line is shifted in wavelength. That's basically it. Why this particular configuration for the neural network? I would say no particular reason. There's you don't really make an optimization study to see what is the best possible configuration for your neural network. Just try something, and if it works, then you get happy. And if it doesn't, then you have to think about some other configuration. So we tried this and it worked. So we got happy and moved on. The training set is also very important for these type of tools. And what we did with the training set is we went back to what we have been doing 20 years ago of using random models. So you generate random model atmospheres and compute synthetic profiles for those random model atmospheres. And I say that we went back to that because most of the work that have been done recently, they take advantage of MHD simulations, which nowadays they are much more sophisticated. And at least for the photosphere, they are becoming very realistic. So we have very realistic simulations of the photosphere, and people have been using these simulations to produce the training set for the neural networks. We decided to do it this way so that we don't tie the capabilities of this network to a particular scenario. We don't have to think whether we're going to be working with observations of a sunspot or quiet sun, or if it's going to be observations at the disk center or near the limb. Instead, because we train it with random models, the hope is that it will work equally well or equally bad in different scenarios. So we think it will probably have a better generalization capability. And what we do is we take 1 million variations of 4 different standard reference models from the 70s and the 80s. We take these models and compute 1 million realizations by adding random perturbations to them. We take 1,000 of these points and take them as a validation set, and the rest of them we use them for the training. I'm going to skip this part. And then when you do that, this is what you get in the validation set. These are 9 parameters that the neural network is asked to retrieve. So these are the temperatures at the base of the photosphere, and then -1, -2, -3, -4. The 3 vector magnetic field components, and the line of sight velocity. So this is an indication of how well the neural network is able to retrieve the model parameters in an ideal situation. And by ideal, I don't mean the data has noise, but it's ideal in the sense that the underlying physics is well captured by the model, and that's an assumption. So in real life, things don't have to work like that, because your model atmosphere has some approximations there which may not hold in the real situation, and so that might introduce complications when you go to real data. So with this kind of tools, it's important to realize that performance with synthetic data, a good performance with synthetic data does not guarantee that they're going to perform well when faced with real observations. So we did some tests with real observations, and for that, it's not easy, because these what we are retrieving here is actually there's quite a bit of information about the thermal structure of the atmosphere. We have information of temperature at different heights. And if you go to Hinode and you want to take a map with high resolution, and you want to compare, there's not a lot of previous inversions with traditional techniques that you can compare with. So I did this work in 2011 where I inverted Hinode data cube. This is a map of a very quiet sun region. What you see here is granulation. This is what you see. Basically, if you were to look at the sun with very high magnification and in white light, you would see this granulation, bright granules and dark intergranular lanes. This will be like I said, the base of the photosphere. And then higher up, you have here -1, -2, and -3 in log tau. Sorry, I just realized that this might be a bit confusing, because this is the plot, the panel here on the top is the base of the photosphere, and then these are higher heights in the atmosphere as you move down on this figure. Sorry about that. We did it this way because it's in optical depth. You go from larger to smaller optical depth. Anyway, so this column here is the inversion that I did with Nicole 10 years ago. Nicole is an inversion code that is based on least squares fitting. like I mentioned in the introduction, this traditional approach. And this is what you get with the neural network. And you can see that it looks very much like the other one, except it's less noisy. I'll show you more about that now. And these are some other parameters. This is the magnetic field in the vertical direction, and this is the velocity. And this is the temperature at -4, at log tau -4. So let me show you an enlargement here to see some details. Here on the left is the Nicole inversion, and on the right is the neural network. And you can see that they show basically the same structure, except that the Nicole inversion is much more noisy. And this has to do with these limitations of chi-squared minimization techniques, where a given pixel, you might not reach a solution that is completely consistent with the pixel next to it, because along the way down the hypersurface, the chi-square hypersurface, they might have gone through different paths. Whereas with the neural network, you don't have that problem, so it looks much cleaner. This is a fairly well-known property of neural networks. They're very good noise filtering machines. And then another thing that's actually quite puzzling is that it's slightly brighter. You get systematic hotter temperatures. So we are not sure why that happens. And so we have to introduce some calibration, but these calibration coefficients to sort of, when you go from ideal synthetic observations to real observations, we find that there's this mismatch for some reason. Like I said, the real world is more complicated than your model, and this sometimes confuses the neural network. So we have to apply these correction coefficients, and they are applied to, and this is another reason why we didn't want to publish the decreased model until we have been able to do something like this and verify that if there's, like fine tuning that needs to be applied, like in this case, then we want to know it in advance. So these coefficients are applied to all of the results that I'm going to show later, okay? Now, one of the big things here is that Nicole took 5 hours working on a workstation with 8 cores in parallel to do this inversion. And the neural network did it in half a second on my laptop. So that's very cool. It's exactly one of the things you're looking for. You're looking for something that's really fast, and you can use it almost as a part of the pipeline of an instrument, because it's so stable and it's so fast, and it gives instant results. So it's really nice. Now we've also compared with the Hinode standard inversion code, which is called Merlin, and this code has this code is a very simplified inversion technique that doesn't give you information about the temperatures at different layers, so you're much more limited, but it gives the magnetic field. So in order to test it and compare the magnetic field, we have to go to a different observation. We have to go to active regions where you have magnetic fields, and you can compare what you get. And this is, again, a comparison of what you get with Merlin, the Hinode inversion code, and with our neural network. And this is the magnetic field in the vertical direction and in the X and Y horizontal directions. And you can see that they look very similar. These are scatter plots. And remember that these scatter plots don't reflect just the error of the neural network. They reflect the difference between 2 inversion codes. So both errors are combined here. The scatter that you see in this plot is due to the error in the neural network plus the error in the chi-squared minimization code. So we have this active region. We also tested with another active region, which is this one here. So there's 2 different active regions at 2 different locations on the sun, and you can see that the results are very much comparable. One of the criticisms that is often employed when people who are used to least squares inversions and they criticize neural networks because you don't get the fit. When you do a least squares minimization, you can look at your fit and see if they are good or bad fits, and that gives you some intuitive idea or some insight about whether your inversion was good or not. And that is true. But here in our technique, because we have the information of the temperature at 5 different layers, we can actually reconstruct the stratification of the atmosphere by interpolating between these 5 points. And we can then produce a synthetic profile very easily. Once you have done the inversion, then you can take the result and compute synthetic profiles. And you can do something similar to a fit. It's not the same concept. This is not a fit, but it gives you an idea of how the model that you have obtained, how closely does it match the spectral observations that you have. And what you can see here is the blue line represents the observations, and the orange line represents the profiles that we synthesize with our neural network inversion. And this is a typical case. This is the average profile observed and the average synthetic profile. This is a typical case where the chi-square is equal to the median over the whole field of view. And this is a good case where it's equal to the median minus sigma. And this is a bad case where it's the median plus sigma, or the representative good and bad cases of fits respectively. I keep calling them fits, but remember, it's not a fit. It's just you take the final result of your inversion and then you synthesize a profile and compare that to the observation. And then one interesting thing is that you can, when you do this is for the quiet region. When you go to the active region, you have very weird profiles, and some of them have not been seen by the neural network. They were not in the training set. And we wanted to see what happens when you have what we call anomalous profiles. And here is an example of an anomalous profile where you have intensity and polarization, I, Q, U, and V. And what you have here is actually a mixture of components. You have in your pixel, you have like 2 very different atmospheres. One of them has a very strong downflow. Probably, I haven't calculated it, but it might even be supersonic. That gives you this extra feature in the red. You can see it here very clearly in Stokes V, but also in the intensity, there is an enhanced red wing. That's because there's another very strongly redshifted component. This has not been this is very different from the models that we had in the training set. And yet, because the training set was done randomly, I think the neural network has been able to do a good job in not panicking, not giving something crazy when faced with this profile, but instead it gives you a fit that is probably a good representation of the majority component of the atmosphere. So this is very encouraging, actually. It's this robustness of the behavior to these issues. And then we have some things that we don't understand well and are the problems of this technique at this point. One of them is why we need these calibration coefficients. We will have to do an extra calibration when we apply to observations. We're not sure why. It has to do with the network. It has to do with the observations not reflecting exactly what was in the training set. So our training set is not a very good representation of reality, but yeah, we are not sure exactly why. And then we have encountered this issue of some sticky values, we call them, which we don't understand very well. This is a scatter plot of velocity in the horizontal axis versus temperature at log tau -2. This should be this is actually a well-known behavior. It's called a reverse granulation. It gives you some anti-correlation between these 2 quantities, and you would expect a cloud of points spread more or less like this. But then you have like this line here where there's a higher concentration of points. Somehow all the points in this region have concentrated here, as if zero velocity acts like a magnet for surrounding points, and we don't understand that very well. It's not necessarily a bad thing. This might be actually part of the uncertainty, but it means that your points are not evenly spread over your uncertainty region, but they might get clustered around some magic value like 0 here, and we are not sure why that's happening. Anyway, and I'm going to spend now a few minutes telling you about the results, which is probably the most interesting things. So this first part of the talk has been about the tool itself, which I think is interesting because I'll discuss this in the conclusions. But then we went and applied this tool to observations of Hinode, because as I said, we still don't have decreased observations. And we got things like this, which I think is very, very nice. This is an active region. The arrow is pointing to the limb, so you can tell which way is the solar limb. The disk center would be in the opposite direction. And what you can see here are maps of the temperature at different layers. So this temperature -1, -2, -3, and -4. And this is compared to Hinode's narrowband images in the G band and in the line, the calcium H line. These are also images that Hinode produces routinely. And so you can, I think this is the first time that there's such high resolution, large field of view images of the temperature in the upper photosphere. I think this has been done before only on a pixel by pixel basis, but not on these large maps. And the first thing I think is that these images are very beautiful. I think you have these sort of very fine network of bright points in the photosphere. This was well known. This is called the facula, and it's due to the presence of very small scale magnetic flux tubes or magnetic elements smaller than the resolution elements in these pixels, and we see them as bright because of just how radiative transfer works. But then when you go higher up, this structure changes entirely and you see different things. And we don't know exactly why you see these things. And this is, like I say, it's probably the first time that we are seeing this, because I think you can compare, I mean, this G-band image, it looks quite a bit like what you see in the temperature at log tau -1. So a little bit above the surface. And I think the expectation, people had the expectation that these calcium images were sort of, will give you the temperature a little higher up, but they don't really look like the images that we find for a little higher up. In fact, these calcium images, they look very much like the G-band images, except that these bright points are small elongated filaments. They are turned into small elongated filaments. Of course, this is a non-LTE line. And in order to interpret this line, you know, it has a photospheric contribution and a chromospheric contribution. So you have both of them mixed here. But maybe interpreting this as just looking higher up in the atmosphere, maybe it's not a good way of thinking about it. Or maybe it's not representative of these intermediate layers at -3 and -4. It's more like a combination of things lower down and higher up. We looked at a different map, another active region, and again, something similar. This is a couple of spots, and these are a bunch of pores here, magnetic pores, and you can see this network of this bright network here. Very, very cool. One of the first things that we notice here, and I think this is the first time that is being seen, is the presence of these reverse patterns. This is an enlargement of the region that of the plot that I showed earlier. We're going to compare the temperature at log tau -1, which is about maybe 100 kilometers above the surface, and log tau -4, which is probably about 400 kilometers above the surface. And well, you see that they're different. You have this facula structure here. Okay, this is well known. But what's funny is that the distribution of brightness here seems to be the opposite as it is here. For instance, if you look at this this region here where you have facula, it shows us a shadow here. It's dark. It's surrounded by a bright environment, but this part shows dark. Okay, and same here. You have this bright region, and it appears dark here. Okay, and vice versa. You have on this picture, you have all this region is bright, and here it is dark. And similarly, you have bright here, dark here. If we look at the other region, we find the same effect. You can see that down here, this is pretty much dark, except for this bright filament here from the facula. Whereas here you have just the opposite. This is all bright, but you can see there is a shadow here. And this shadow matches exactly this bright filament. Or here you have this bright filament here, which shows us dark in this region, embedded in a bright region, but there's this this dark filament. Same here around this pore. You have this is pretty much dark, most of it, and here it's pretty much bright, most of it. And up here you have I forgot the name, the facula here, which is bright, and just the corner is dark. Here we have the opposite. Where the facula was, we have it dark, and where was dark here, we have it bright. So you can see it visually, but you can also quantify it. If you look at the correlation coefficient, we just calculated the Pearson's correlation coefficient between the two images, and it's minus 0.77 here and minus 0.78 here. This is obtained by taking all the points that are bright in this image or this image, and then look at the correlation between the brightness of these 2 points. And so this is pretty a pretty strong anti-correlation, 0.77 and 0.78, and also they're remarkably similar for two different observations, two different maps. So this is an interesting effect, I think, and it should be explored further. And also, we have these, we encounter these bright arcs. When you look at the pores, let me go back to the full image. When you go to the active region, you have, like I said, you have the sunspots, but you have these tiny pores. Pores are like small, in a way, they're like small sunspots, smaller than maybe 3,000 or 4,000 kilometers in diameter. And they are like magnetic elements, but they are macroscopic. They are resolved in our observations. And if you enlarge that region where you have the pores, you can see that in both maps, the pores have are surrounded by an arc of a bright arc, and these arcs are in the direction of the limb. If you look at the arrow here, this arrow points to the limb. You can see that all these pores have a bright arc in the around the limb side. It's not a circle, it's not a ring, it doesn't go around completely. It's on the side of the limb. You can see it very clearly in this image. It's a little more difficult here because it's more messy, but you can see that all these magnetic elements, they have like a bright arc running around the limb side. And this was very puzzling to us at first, until we realized that this is probably due, this is our interpretation, this is probably due to something called the hot wall effect. The hot wall is an old model prediction originally made by Sprout in the 70s, and then more sophisticated models by Knolker and Schussler in the 1980s. These were developed as models, small flux tube models for these unresolved microscopic magnetic elements that form the facula. And the idea, this was an attempt to try to explain something weird observed in the facula, which is that the facula are brighter than the surrounding surface, but the contrast between facula and the quiet surface changes from the center of the disk toward the limb. And this variation could be explained by this simple model in which you have a magnetic element. The magnetic field is like a vertical cylinder, and because of the presence of the magnetic field, this cylinder is partly evacuated. So the gas density here is lower, and so is the temperature. And so because this is partly evacuated, there's a Wilson depression. That means when you look, the surface, your tau equal 1 surface on the quiet sun is here, but then because this is evacuated, you see a lower height. And because you see a lower height, and because here temperature increases with depth, when you look at an angle, if you look from this direction, in the direction of the limb, your line of sight is going to hit this wall, and this wall, because you're looking at the deeper layer, this wall is going to be hotter than when you see when you're looking up here. So the facular contrast was explained by this model, this hot wall model. But these, of course, these elements are too small to be resolved in observations. We cannot see them. So this hot wall had not been seen directly. Only, it's an explanation to the variation of brightness in the facula. And I think what's happening here in our observations is that we are seeing exactly this for the pores, because the pores are bigger than the magnetic elements of the facula. We're seeing this effect in a pore, and we can see the hot wall only on the limb side. And that will be the explanation of why we see those bright arcs surrounding the region. And with that, I'm going to conclude. I'm only 2 minutes late, so I'm pretty proud of that. But yeah, I wanted to tell you all about this tool, which I think might be of interest for our solar colleagues, especially given that we have these wonderful instruments coming up that are going to produce very large data sets. And this tool can be easily adapted to future observations and telescopes, even like the EST. It's got good generalization capabilities, and an interesting thing is that because we don't rely on simulations to build a training set, this might be suitable to do something like this for chromospheric observations. This is actually our next item in the to-do list. And well, I wanted to mention some problems with this, but I'm going to leave it for some other talk because I'm out of time. But I think because we are publishing all the codes and all the tools, not only the neural network itself, but also the building of the training set, I think this could be also useful for anybody who is doing interpretation of spectroscopic observations. So if you just take this and create your own training set for, I don't know, you can use it for stellar spectra, or even for, I don't know, quasar spectra or whatever. The idea would be that if you replace the training set, the part where you take the model and compute synthetic profiles, you take out the model to compute solar profiles and replace it with a model to compute with a code to compute stellar spectra or whatever spectra you're working on, then you might be able to use the rest of the tool. And then I think it's very cool that we apply these to observations, and right away, just with the first application, we found new things that had not been seen before, like this hot wall effect, which is very cool because it's an old prediction from dating back to the 70s. And I think we are seeing it here for the first time in direct observations. And then there's this puzzle reverse facular patterns that we don't understand. And it's very puzzling because common wisdom tells you that it's the magnetic fields that carry the energy from the lower layers to the upper layers. And in fact, 80% of papers in the solar physics community have to do with how the chromosphere and the corona are hotter because the magnetic field is taking energy from lower down and taking it up with some mechanism. And what we are finding here is that there's places where you have magnetic fields in the lower photosphere, but then in the upper photosphere, at the same location, that atmosphere is not hot. It's cool. In fact, there's like an anti-correlation. So this is very surprising. It even, like I said, it goes against the intuitive notion that we have in solar physics. There's even this idea of the magnetoacoustic portals that was put forward by Jefferies et al. In 2007, where actually these small magnetic elements, they can act as propagators of oscillations, magnetoacoustic oscillations from the lower layers to the upper layers. So one would expect that where you have a magnetic field lower down, that should be hot also in the upper layers. So this is a surprising result, and I think it should be investigated further in the future. Thank you very much. With that, I conclude. And now, if you have questions, I'll be happy to take them.
Thank you. Thank you. Don't worry, you will still have like 10 minutes for questions. So no worries about it. So yeah, anyone, please raise the hands. Her hand. Anyone willing to ask any question? I see no hands raised yet, even though we have quite a fair large attendance. We have almost 30 people.
That's because I'm very clear in my explanations. Thanks to me a lot.
Yeah, I'm a bit surprised. I was expecting. Here's a question here. Who is this? Andres, I think you can unmute now.
Yeah. Hi.
Hi.
I have a question. Well, thank you for such an interesting talk. Is the network applied to the whole image or pixel by pixel?
Yeah, that's a very good question, and I forgot to mention that it's. I think one of the interesting things about this technique is that it's applied pixel by pixel. So each pixel is treated independently. It doesn't know anything about the other ones. The neural network works only on one pixel, one spectrum. You do the inversion, and that's it. You go pixel by pixel. Yes.
And if it's applied pixel by pixel, did you apply some sparsity or regularization to obtain a correlation between neighbor pixels or something?
No, I didn't. So it just comes out naturally. That doesn't mean you can take the smoothness of the solution as a guarantee that it's correct, because what happens is that of course, the neural network maps some inputs into some outputs. So if your inputs vary smoothly, your outputs are also going to vary smoothly. One has to be a little careful with that. But yes, the fact that you get consistent results is encouraging.
Thanks.
Thank you.
Andres, more questions? I see no. Let me check the YouTube channel in case there's somebody writing a question there. No, there are no questions in the YouTube channel. Yeah, no more questions. Okay, Hector. So I think this is it. Thanks a lot for the effort of putting together this talk in this very busy time. And yeah, and thanks for the audience. I think we hit a fair large number of attendees today. I'll talk to you. So this Thursday, as you know, we're going to have the Día de Nuestra Ciencia, the Day of Our Science. So we'll be busy and we'll have no regular seminar. And I think that next week we will start our regular seminar calendar again. So thank you, everyone, and I'll talk to you very soon. Bye-bye.
Thank you all. Bye.